So what we've learned is the general formula, right? The weight for all objects due to the Earth is equals to the mass of that object times this acceleration due to gravity constant. And this is our analysis of anything in free fall. And when we say something is free fall, it means that the net force is equals to the weight only. So i.e. the weight is the only force on that object, and that's called free fall. And then the general analysis of that is, well, we have Newton's second law over here. So Newton's second law tells us F equals to ma, and it's you'll see more and more. I would used to write it like this because usually we're interested in solving for a, and when you're interested in solving for a variable, which side do you usually put it in math? Usually put it on the left, right? It rolls off the tongue when you say F equals ma, but usually in 90% of the cases you're trying to solve for a. Okay, so yeah, so Newton's second law tells me that, and from because I'm analyzing free fall, so F net is equals to W. If I'm being diligent, I'll copy that. But usually on the left, there's also benefit if there's nothing changing on the left-hand side, there's no algebra you're performing, you can just leave that blank. That's just a generic way in mathematics, right? And we know that here is the formula for W, right? So W equals to mg. And now, in principle, I don't have to write this as well, but the next thing I want to do is I want to cancel the m on both sides. So to do that, it will be a little bit nicer if I now copy this down because it's more obvious that I can cancel the m on both sides, which gives me a equals to g. Okay, so like I said at the end of the previous video, not really a justification why everything accelerates with g, because that's what you used. It's a circular argument. That's what you used to get W equals to mg. But anyway, this is the general analysis. If you like, you can flip it around and say, let's accept that W is equals to mg, and in that way you can quote unquote explain this. So I'll still sometimes say this explains why everything falls in it, but just understand the philosophy behind that. Okay, so now this brings us to the second question we asked, and with a book and a paper, right? So now every one of you know that the book will reach the ground first, right? So normally that is the case. But why is it? Because now that just contradicts my whole analysis of me spending 10 minutes over here talking about free fall, that all objects accelerate with 9.81 in downwards direction. Maybe I should clarify that as well, downwards, right? Or towards the Earth, right? And that's because the force over here of W is pointing downwards. That just seemed to contradict that. So what's going on? And I think this is a very obvious solution to a lot of you because this here ignores air resistant, and we do have air resistant. So now let's get one level deeper and understand why or how does the air resistant come into play. Well, what that means is, now let me put in the air particles. I can't draw millions of air particles, so let me just draw, let's say 5 little particles, and I'm going to zoom in and enlarge them a little bit so we can actually see them. And assuming, right, they are the same size of a book, and yes, the same dimensions, so they sort of encounter the same number of air particles as they fall. So can you draw a free body diagram on both of them? Well, yes, yeah, I know how to do that. First, I need to draw my contact forces, right? I draw the center of mass of the object, and then the contact forces, well, it's contacting these air particles. So each little air particle will produce a normal force, and it's contacting it on the bottom surface, right? So it will produce a normal force upwards, but it's a tiny normal force. Let me use a different color. Yeah, so I'll have 1, 2, 3, 4, 5 like this, right? From let me make our air particles blue, like this. Okay, and okay, good. So what else is it in contact with? Nothing much really. So it will. There is also the gravitational force, right? So I also have its weight. Okay. Let's draw the other one as well. So let's do the same. So I have the normal force. 1, 2, 3, 4, 5. Okay, they should all come from the center of mass, but I want to displace them a little bit so we can actually tell them apart. And let's draw the weight. Now, when I draw this arrow, obviously pointing down, but what size should I use relative to this? I don't need to be accurate, but just relatively. It should be a much smaller one, right? So I'll draw a much smaller one over here, and let's call this W prime. So we know that this W does not equals to that W. Okay, well, what do I know? What can I say about the little blue arrows? Well, those are the force or the normal contact force on the object by the air particles. And they will be exactly the same in this two cases because the air does not know that what are you putting on top of it, right? The air it does not have its own mind. It will not say, hey, if you're putting a heavy book on me, I'm going to put more force on you than the other. If you're putting something light, let me change my mind. I'll change the force that I push on you. The air does not do that. So each little air particle would do whatever it does. It produces a tiny bit of force. Collectively, that is exactly what air resistance is. So all these little arrows add together collectively. The net effect, it's called air resistance. Okay, so I've justified why they should be the same on both sides. Okay, if you like, I'll call them collectively A, for capital A for air resistance. And okay, how about W? I know something about W. I know a formula, right? That's mg. And here is mg. Now, be careful. Again, another tip about solving problems is, can you see immediately what there should be alerts that come up in your mind when you write this? It's because I'm using duplicate variables. Okay, whenever you repeat a variable, you should ask yourself, is this m the same as this m? And the answer is no, right? So this, I should put m prime like this, okay? And then you should ask, is this g the same as this g? Should I put a g prime over there? Well, no, I don't need to, because in this case, I do have a good reason that they are the same, the same value, right? It's from my important fact, or the greatest mystery, right? I don't know why, but it is that case. So yeah, so the G is the same, and that applies. This is a general philosophy for everything. Like whenever you see something that repeats themselves, ask yourself, is this A the same as this A? And in this case, yeah, I just copied it down, right? So I have a good reason for things to be the same. And yeah, there we go. So in fact, this is now, I think you understand why one thing accelerates so much faster than the other. Let me emphasize that this is so much more massive. I'll use a capital M. This number, so this is so much larger than this. If you have 1,000 pages, right, this will be 1,000 times larger than that. So the G is the same, which means W is much, much larger than W prime. Okay, so what is the net force? So the net force on this case, in this case, I should say, is, well, let's analyze the free fall situation all over again, right? The net force is W minus A when I'm analyzing everything in the downwards direction, right? Okay, so everything in the downwards direction, everything is in one dimension. Remember, I can use the quick way of adding vectors or finding net forces in 1D. I don't need to put out all the vector machinery, but just need to take into account of the minus signs, right? So I'm looking downwards, right? And MA, in fact, I should use capital M if this is, right, if this is the mass of it, right? So I'll put capital M as the mass of the book, right? So MA is equals to this, you see that W should be much, much larger than all the forces on the object by the air particle. So this is almost like free fall, right? So if this is small enough, then this is almost like just W, if W is much larger than A, okay? And you basically have a free fall situation over here, right? So it's basically, right, capital MG, and you basically have this, all right? So well, first of all, yeah, this is not a free fall anymore in this state. It's just approximately free fall. Free fall is if F net is just W, right? So in this whole question 2, these are not free fall and not completely free, at least. And more, especially for this one. Now we can do the same analysis, right? And look at the net force on the prime object. And in this case, again, same thing with here. Now notice I use the same A because it's the same air resistance. Like I said, the air particles do not care about what the mass of that object is. It does depend on some things. It does depend on the area. If you have a larger sheet of paper, you will have a larger air resistance. And the reason is just simply because you have more little arrows, right? You have a lot of these little, you have more particles supporting it, pushing upwards. So yeah, the air resistance depends on some things. It depends on the dimension. It depends on the shape of the object a little bit. But now I chose a specific case to make things simple in this case, that they have the same cross-sectional area, the same shape, and then the same area as well, as far as the air particles are concerned. So, right, so you can do this, but this time, as you can see, if I add all these little arrows up, if I add up 1, 2, 3, 4, 5, right, they sort of just about counteract the W, right? So I can say M prime A, M prime G minus A, and then I have A is equals, this is equal, not approximately, G minus whatever that is. But essentially, you see that the acceleration is G, but it's subtracted by something. So the answer will be less than G. Okay, so the acceleration, right? So this is 9.81, subtract by something, it will be less than G. So the acceleration here would be approximately G. Acceleration here will be less than G, which means this will accelerate much, much slower. And depending on how much air particles you have, it will go very slowly. Okay, so there's a couple of ways to get around this, that you can test Newton's law in your house. First of all, one way is remove all the air particles. So if you can find a way to remove all the air in your house and do not suffocate, then you can test this out. And in fact, I'll see if I can find some videos for you to show you people have done this in outer space or even in a vacuum chamber on Earth, and drop things and see that they do, even a feather and a hammer can fall exactly at the same rate because you've removed all air and there's no more air resistance. So free fall does work. Well, at home, that is not practical. What's another way? Well, you can take the same heavy book and compare it with how do I reduce the air resistance other than removing the air? Well, if I have a very, very small area, then you can probably get around that. So for example, you can at home find another small object instead of a piece of paper, maybe a paper clip or something like this, and a file clip, and take a textbook, take any book you have. I don't want to destroy the ground right here or have someone come up and complain to me, but you can try that at your home and drop both objects at the same time, and you'll see that they will reach the ground at the same time, because here, like I said, the mass is so much more overwhelming than all the masses of the particles. So it's not gonna, it's gonna be a very small air resistance anyway. And you can also create a very small air resistance by having a small object, so you have much less air particles supporting it. That's another way. It's also one last suggestion I can give for you is if you take your piece of paper and take a book of your choice. Now, how do you eliminate the air particles over there? Well, one way is put your paper on top of the book. I do not have one that is exactly the same shape, but try to do it exactly the same shape so you don't have extra air resistance over here. So that's what you want to do, and release this at the same time. Okay, so I'll let you try this at home, right? I have extra air resistance over here, but you can try to find either a bigger book or a small piece of paper and put it on top. Now, if the paper does, if it does fall slower, if it accelerates slower than the book does, then even if you put it on top, then what will happen is the book will, the book will fall first, and then the paper will fall slower, as if when you do it separately like this. However, if Newton is correct, right? If our theory is indeed correct that W equals to mg and that all things fall at the same rate, this is a way to eliminate the air resistance, because now you have basically no more air resistance. If this is the same dimension, then there's no more air resistance pushing on the paper, right? Because your book blocked it out. And the air resistance towards the book is very negligible, as we have justified. All right, so I'll let you try that and let me know how it goes.